Okay, so let's start today's class. First, we'll be doing a revision of what we saw yesterday, and then we will proceed with today's topic. Okay. Okay. So let's start with what we covered yesterday. So what was the first topic we covered yesterday, guys? So tell me the topics, and we will do a quick revision. Yes, we started with box plots. Okay. Why are box plots used? Box plots are used to identify outliers in data. Okay. We all understand what outliers are. Outliers are values which are very different than the rest. Okay. So a student who scores exceptionally well, or quite better than the rest of the class, is an outlier. Okay. And outliers is not something bad, it might be something very good also. Okay. Something which is very different from the average, that is what is an outlier. Okay. So boxplot is a way of identifying outliers. Okay. How do you identify outliers? Boxplots will not help you to get rid of them, it will just help you to identify. And obviously first identification is important, only then you can remove it or change it. Okay. And why is it so important to identify outliers? Because later we will see a lot of machine learning algorithms, a lot of ML algorithms, the algorithms, they are negatively influenced by outliers. We will see that, of course, once we start with ML. But for now you can just remember that it negatively influences the algorithms, which is why it is important to identify the outliers and also to get rid of them. Okay. When I say get rid of them, that not necessarily means deleting them. It might mean changing them, or maybe deleting them if they are very few in number. Okay. So boxplot helps to identify the outliers. So how does it look like? So it looks like a box. Okay, so I'll draw a box. It looks something like this. So I've drawn it horizontally. So this is a box. 50% of the data is contained in the box. Okay, 50% of the data. And it has a few lines like this, which are known as whiskers. Okay, has a few lines. Okay, now guys, tell me, the variable will be in this axis. The variable is on this axis, whatever is the variable. Okay, let's say this might be sales. Now what is this? Tell me, guys, what is this? What is this? Yeah, so what is this point? What is this point here? Yeah, this is Q1, which stands for 25th percentile. Which stands for 25th percentile, and this is Q3. Okay, yes, Satish, you are right. This is Q1 and Q3. This is also known as first quantile, third quantile. And at the center you have the second quantile, which is the median. Okay, and this distance that you see here is known as interquantile range, IQR. Okay. Okay, and what is this distance? What should I write here? Somebody tell me, what is this? Yes, guys. Yeah, so this distance is from here to here is 1.5 times IQR. 1.5 times IQR. So if you have to find out what is this, let's say the origin is somewhere here. Okay, so this is sales, this is the origin. So I know that this distance is 1.5 times IQR. But what is this? If I have to find from the origin, what is this? Then what would that be? This one? You will have outliers somewhere here, and similarly somewhere here. So this is nothing but we know that this is q1. Okay, and we know this distance is 1.5. So this is q1 from the origin. Okay, this q1 will be some value. Let's say this is 5. Okay, that means from the origin this is 1, this is 2, this is 3, this is 4, and this is 5. Okay, something like this. So if you need to know what is the value here from the origin, what you have to do is just take q1 and subtract this distance from it. Okay, this is simple geometry. So this one will be q1 minus 1.5 IQR. Now why are we so interested in knowing what is this? Because this is actually the purpose of boxplot, right? This will tell you that whatever is below this is outlier. Now visually it will show you what are the outliers. But let's say you have to identify in your data frame. You have a data frame where you have the values. So it will show you that there are 4 outliers, let's say. Now which 4 of them are outliers? How would you know? That will not be shown here. So to know that, you will have to find out this threshold, and then in the data frame you can find out the threshold. Okay, df, then df, the column name is less than the threshold. Then that means this way you can identify the rows which are outliers. Okay, so identifying this threshold is important, so that you can get using q1 minus 1.5 IQR. Similarly, identifying the threshold on the upper side from the origin, we know this is q3 and this is 1.5 IQR. So this will be q3 plus 1.5 IQR. Okay, remember we are trying to know its value from the origin. Okay, from the origin. Okay, so I think this is all about box plots. Any questions on box plot? Any questions here? Anybody? Okay then. So what was the next topic? What was the next topic we covered? Okay, z test. So z test is nothing but finding the z value. That itself is known as z test. So whatever z value we saw yesterday, finding that value itself is a z test. Okay, when you calculate the z values and then try to make decisions, that is called, this entire thing is called z test. Okay, so what is z value? Yes guys, tell me, what is z value? What is the formula? First tell me the formula, and then, or maybe you can tell me the formula in English or in maths, whatever you remember. Okay, so Satish says distance from mean in terms of standard deviation. Okay, so that formula might look very innocent, but it has a lot. Okay, that definition, distance from mean in terms of standard deviation. Okay, so that means, and this only applies for a normal distribution. Okay, this applies for a normal distribution. So let's say we have this normal distribution. Yes, Satish, that is correct. Okay, this is a normal distribution. We know that the average lies somewhere here. So this is my mu. Now we have to calculate the distance from the average. Let's say I have a point here. I have a point here. So we have to calculate the distance from average. So I'll calculate this, the distance of this point from the average. Okay, so the distance is here. This is the distance. Okay, now this will be the distance in whatever unit. Let's say we are talking about age. let's say this is age variable. I have drawn a histogram for age. So all of you remember, right? This is nothing but a histogram. So instead of bars, I have just drawn a curve over the bars. So this is nothing but a histogram of age. Now I know average age is, let's say, around 30, and I want to find the z value for 20. Okay, so let's say for x is equal to 20, I want to find what is the z value. Okay, so 20, I have 20 will be somewhere here. Okay, below the average. So 20, I want to know what is its z value now. So I know the distance. Okay, I will also need to know the standard deviation. Let's say standard deviation for this distribution is 5. Okay, so what I have to do now, I have to calculate first the distance. So the distance is 10. I can clearly see. How did I calculate the distance? I just did this distance basically. So either you do mu minus the x value or x minus the mu value, whatever. So I know the distance is 10. Okay, the distance is 10 now, but I don't just need the distance from mean. I need it in terms of standard deviation. So now this value is how many standard deviation. I have to find that. So how many standard deviations is this value? So you know the standard deviation, just divide it by that, and you will know that this is 2 standard deviation. Okay, so this is 2 standard deviations from the average. Now since it is below the average, I will add a negative sign. Otherwise, similarly, you will have a point here also, which is, let's say, 40. 40 will also have a z of 2, but that will be positive because that is more than the average. This is less than the average, so it will be minus 2. Okay, so this way you can calculate the distance from mean in terms of standard deviation. So if you have to get the formula for it, it is very simple: xi minus mu divided by sigma. Okay, so now you put it in the formula. Xi is 20, mu is 30, and sigma is 10. So what you get is minus 2. The same thing. The same thing. So you don't need to actually remember the formula. You can just calculate it using the concept. Okay, so this is z value. Okay, this is z value. Now remember, we had discussed in the previous week that, so how many of you remember, no matter what distribution you have, okay, your data will be all your data will be within a few standard deviations from the average, right? Do you remember, guys? No matter what kind of distribution you have, your entire data will be within few standard deviations away from the mean, maybe 4 or 5 sigmas away from mean. Okay, this was true for any distribution. This is true for any distribution. And for normal distribution, what had we seen? For normal distribution, what had we seen? Yes, guys, tell me. This is important. We have covered this in last week. For normal distribution, what had we seen? All your data will be within. Yes, within plus minus 3 standard deviation. So for a normal distribution, it will be 3 standard deviations away from mean. Because we know, right? If you go x bar plus minus 3 sigma, you get 99.7%. So this is like almost everything, right? So for normal distribution, this range reduces. This range reduces further. If you take any other distribution, you take any random distribution, let's say it is like this. So here, if this is the average, your entire data will be, maybe this is 1 standard deviation, this is 2, this is 3, and maybe this is 4. Similarly, 1, 2, 3, 4. Okay, or maybe max 5. So within 4 to 5 standard deviations away, you will get everything. Okay, but for a normal distribution, that range is smaller. That range reduces to only 3 sigmas. So 3 standard deviations away. Okay, now I have a tricky question here. Let me see who can answer. I have already added it to the LMS, but let me ask. So I tell you that the average price of a, let's say, of a house, the average price of a house is, let's say, 20 lakhs. Okay, and standard deviations is, let's say, 10 lakhs. Okay, the average price of a house is 20 lakhs and standard deviation is 10 lakhs. Now I ask you, is the house price following a normal distribution? Tell me, guys. Is the house price following a normal distribution? So until now I have been giving you the distribution and then asking you about the range and all. Now I have given you the range and I'm asking you, is this following a normal distribution? So average price of a house is 20 lakhs and standard deviation is 10 lakhs. Now I'm asking you, are the prices following a normal distribution? Tell me the answer, yes or no, and why do you think so? This is a tricky question, okay? So think. Yes, guys, you can try. It's okay if you don't give the correct answer. At least try. Tell me, everybody. I want to hear an answer from everybody. Okay, Mukesh says no, it will not follow a normal distribution because standard deviation is too high for house in terms of price. No, but Mukesh, standard deviation is a constant. I have given you its value. Okay, so I don't think this is the reason why it is not a normal distribution. It is a standard deviation, so it is 10. I found it using all the price of houses, right? So I don't think that is the reason why it is not following a normal distribution. Maybe something else is. Think. Take your pen and paper and try to draw the distribution. How would it look like? You just need to know whatever we have learned so far. Anybody else wants to try? Okay, let me help you guys. Okay. So what have I written? That the average price of a house is 20 lakhs. So this is 20, and I have written that the SD is 10 lakhs. Okay. Now the question is the house price following a normal distribution? Let me draw a normal distribution. Let me draw a normal distribution. So this is a normal distribution. Okay. So let's say that yes, it does follow a normal distribution. So I'll draw a normal distribution and this is 20. Okay. And I have been given that standard deviation is 10. So if it is a normal distribution, what can I say about it? I can say that if I go one standard deviation on both sides, I should get 68% of the data, right guys? So one standard deviation on both sides will be 30 and here it will be 10, right? Here it will be 10. So that means within this range I should get 68% of the data. Okay. Okay. Maybe I don't know about it, so it might be 68%. Okay, let's move further. Then I know within two standard deviations I should get 95% of the data, right? Within two standard deviations away. So let me go two standard deviation away. So further 10 units if I go, I'll get 0. And similarly if I go further, I'll get 40 here. Okay. So within this I will have 95% of the data within this. Within this, I will have 95% of the data. And after this, if I go 3 standard deviations, I will get 100% of the data. But do you think I can go further on this side? Do you think something exists on this side below price 0? Below price 0, do you think something exists? No, I cannot go further. Even the price of 0 doesn't make sense. You will not get the house for 0 rupees. So I cannot go beyond this. But if it was a normal distribution, I should have been allowed to go here, because that's what a normal distribution says, that if you go 2 standard deviations, you get 95% of the data. But I can't go 2 standard deviations. There is a restriction by common sense, because price cannot be below 0. So my common sense restricts me to go below this. I cannot go on this side. This is not allowed. But if it was a normal distribution, I should have been allowed to go there. So what does that mean? That means it does not follow a normal distribution. It is probably something like this. It is probably something like this, where this is the average, 30 lakhs, and everything else is after this. Okay, and this is not a normal distribution. Normal distribution will be symmetrical. So that means this does not follow a normal distribution. It follows something else. So the answer is no. Do you understand, guys? Do you understand this? Everybody, do you understand? So this is the reason, Mukesh. It is not because the standard deviation is too high. It is because given the standard deviation of 10 lakhs, it defies common sense. Because standard normal distribution tells us that if you go 2 standard deviations away, you get 95% data. Okay, but in this case, I cannot go 2 standard deviations away, because going 2 standard deviations lesser than the average gives me a price of 0, which doesn't make sense. So I cannot go 2 standard deviations below the average. Okay, so it doesn't follow the laws of normal distribution. So it is not a normal distribution. It is probably something else. Okay, so in most cases I have seen, usually prices will never follow a normal distribution. Price of anything will never follow a normal distribution. It always follows something like this. Okay, it will generally have a right tailed. This is called having a right tail distribution. Okay, so prices of anything usually follows a right tail, because there will be people who will be ready to pay a very high price for the same stuff. Okay, take anything, for example, price of houses. Your average price of house might be 30, but you will still get houses for 10 crore, 100 crores, whatever. So whenever it is about price, it usually follows this kind of a distribution, a right skewed distribution or right tail distribution. Okay, yeah, so this is about z test. Okay, now let's move to the next topic. What was the next topic we covered? Yes, guys. Yeah, binomial distribution. Okay, so what did we cover about binomial distribution? It is called binomial because we deal with success and failure criteria. Okay, we will only have two options, either success or failure. Next, the trials should be independent. Okay, the different trials, which means the number of times you toss the coin, each toss is one trial. Okay, the number of times you roll a dice, each roll is independent of the following or preceding roll. And then we saw, if n is the total number of trials, and r is the number of successes, okay, and p is the probability of success for one trial, then the binomial distribution tells us that if you need to know what is the probability of R successes in n total number of trials, the formula to do that is NCR p to the power, I'll write the same R here, then I will write 1 minus p, and I will write n minus R. Okay, so this is the formula to calculate. In Python, what did we see? How did we get this formula in Python? We saw it was binom dot probability mass function, right? It was this, right? Right, guys? And what was the first input? So it will take 3 inputs. What was the first input? Yes, it was R. Next was N, and then it was P. So you give these 3 inputs and it will give you the probability. It will give you the probability of R successes in N trials. Okay, this is what it will give you. Okay, so this is binomial theorem. We also saw how do we derive the formula. You don't actually have to remember the formula, you can derive it. Okay, but that is not needed. It is not a very difficult formula, you can remember it. Even remembering is not needed actually. If you just know what is this, or you can Google and find it out, but sometimes you get stuck with Google also, because there are a lot of other formulas also. There is something called as CDF and so many others, so you might get confused, as I was yesterday. You saw, right? I had to Google and wait for some time to get this formula. So it's better if you just note it down somewhere and remember it. Okay, the next topic finally was hypothesis testing, which was the most important topic. Okay, so yeah, what do you know about hypothesis testing then? Tell me, guys. Let's see how much you remember. So hypothesis test is a concept where we start with an assumption and then we calculate that if this assumption is true, what is the probability of getting a result as what is asked in the question. Okay, so in the question you will be given something. Okay, and to either go ahead with that something, there will be two options. Okay, so you will take the default option as the null hypothesis, and you will take an alternative hypothesis which will be opposite of the null hypothesis. Okay, then you will assume the null hypothesis to be true, and then you with that assumption you will find the probability of the alternative, okay, or more in its direction. If that probability is very small, you will reject your null hypothesis. If that probability is not small, you will not reject your null hypothesis. Okay, so for example, you will see if a question is asked, let's say I roll a dice 10 times and I get 4 sixes. Okay, I get 4 sixes. Is the dice fair? So how will I find this? So what will I do? I will take a null hypothesis, which will be that the dice is fair. So I'll say the dice is fair, and that means probability of getting a 6 is 1 by 6. Okay, and the alternative hypothesis will be that dice is unfair. Dice is unfair. Okay, which means probability of getting a 6 is, should I write greater than 1 by 6 or lesser than 1 by 6? What should I write? Tell me, guys. What should I write? Greater than 1 by 6 or lesser than 1 by 6? You're getting 4 sixes, when you roll it 10 times, is that higher than usual or lesser than usual? It is higher than usual, right? Because the probability is 1 by 6. That means 6 times you roll, you might get it once. So going by that logic, if you roll it 12 times, you might get it twice. But in 10 times itself, you have gotten 4. So this is more than usual. So you have been lucky. So it should be dice is unfair and the probability of getting a 6 is higher than 1 by 6. This is your alternative hypothesis. I hope everybody understands this. Okay. Now I will calculate the p-value. I will calculate the p-value now. What does that say? P-value says that you will assume the null to be true. Assuming the null hypothesis, you find the probability of alternative, okay, or more in its direction. Okay, what is in its direction? So here the alternative tells you that probability of 6 is higher than 1 by 6. Okay, that means it might be greater than this. That means your chances of getting heads will be more. Okay, now this will follow a normal distribution. This will follow a normal distribution. Okay, why this will follow a normal distribution, we will discuss that today. Okay, so I'm just take my word for it that this will follow a normal distribution where you roll it 10 times, right? So you can get 0 sixes or you can get 10 sixes. You cannot get beyond 10 because you are rolling it 10 times. You cannot get less than 0. Okay, and you will have maybe around 2.5 2.2 here, which will be the average. Okay, so around 2 you will get by default, but here in the question it is given that you are getting 4, so that means somewhere here. So you have gotten somewhere here. So now what will be the direction of alternative? The direction of alternative is higher than 1 by 6. That means you will get more and more sixes. Not this direction, if you go, this will be opposite. This will be opposite direction of alternative because the alternative says that you get more and more sixes. Okay, so that means this area we have to find. We have to find this area. Okay, whatever is this area, and then we have to compare that area with the threshold, and this area is nothing but the p-value. This is called p-value. This probability is called p-value. So we will find this, and remember this is very similar to the quiz, the probability distribution quiz. Even in the quiz the average was given to you and you were trying to find the probability of a student scoring beyond a number. So these are very similar. Okay, again you have the normal distribution. So now I will calculate this using Python. So I'll just run this. Import the binom function first. Okay, and then I will use the binom dot probability mass function. I'll give the value of r. R here is 4 or more, right? So I'll write 4 or more. So let me do it for 4 first, and then I will write the value of, I'll write the value of n, then n is 10 because I'm rolling it 10 times, and then I'll write the value of p, which is 1 by 6. So this will give me for 4. Okay, so this is the probability of getting 4 heads or 4 sixes when you roll a dice 10 times. Okay, you can see it is 5%, but I need it not just for 4, I need it in its direction also. So for 5 until 10 I'll have to calculate. So how do I do that? I can write a loop. Or I can use Python comprehension, which tells me that instead of 4 just write I, and then write for I in, you can give a list which is 4 comma 5 comma 6 comma 7 comma 8 comma 9 comma 10. Okay, and you put everything inside a list. So this way if I run, I'll get all the probabilities. I just take a sum of it. So this will give me the total area. Okay, so the total area as you see is 6.9%. Okay, I can just multiply it with 100 to get the percentage. So 6.9% is the answer. So the p value is 6.9%. So what does that mean? That means that if a dice is fair, there is 7% chance or 6.9% chance that you will get 10 times, you will get 4 6s when you roll a dice 10 times. Okay, this is what is the meaning of, or is the interpretation of p value, that if you roll a dice 10 times, there is 7% chance of you getting 4 6s if the dice is fair. Okay, now we will compare that with the threshold. Now 7% is not very small a chance, right? You might get lucky and fall in this 7%. So we will not reject. So this is p low, null go. Remember that poem I told you? If p is low, null will go, or you reject it. If p is high, your null will fly, so you don't reject it. So here my p is higher than 5%. Okay, and you compare this with 5%. Okay, so here it is higher than 5%, so you will not reject your null hypothesis. You will fail to reject. You will fail to reject null hypothesis, which means dice is fair. So you will say the dice is fair. I was probably lucky that, or you were probably lucky that you got 4 6s when you rolled it 10 times. Okay, this is not a unfair dice. Is that clear, guys? Do you follow? Any questions, guys? Okay, cool then. So let's start with the first topic for today, which is the central limit theorem. Okay, again, this is something very important, and that's why it is called central limit theorem, because it is central to all of statistics. Okay, this is something very important. So it's called central limit theorem. And again, guys, these concepts which I am teaching you, not a lot of people know about these. Okay, so if you find these very difficult, you can just understand it high level and skip it also. Okay, so I'm not forcing these topics on you, but of course if you know these will be your advantage. Okay, you go to an interview and you talk about these concepts, people will be very impressed. But it's not mandatory for you to understand these concepts. You may be a data scientist, and you may be a very good data scientist without knowing these also, because while at job you don't need to know so much theory. Okay, you need to be more hands on. These theory is not needed, but of course if you know, this gives you the edge. Okay, so if you find these topics very difficult, feel free to just understand them high level and skip it. Don't spend a lot of time on these, because these understanding these topics takes time. Okay, so give yourself that time. Don't think that until I understand this topic I will not move ahead, I will not move to the next topic until I understand this. Don't do that. Even for me it took some time to understand these topics. Okay, so try to understand them high level and then move ahead, move with the class. Don't say that no, I haven't understood central limit theorem, so I will not move to the next topic, which is linear regression, because I'm yet to understand central limit theorem. Don't do that. Always remember, guys, don't do that. Understand them high level. later you can come back and dive deeper here. Okay, because in the industry, if you ask these, no, not hardly 10% people will know about this. Okay, but in the interviews it is sometimes asked. So if you understand these and you go to in any interview, and let's say you are lucky that these questions were asked, then you will realize its importance. And I probably wouldn't have known about these topics. I wouldn't have remembered these topics if I hadn't been taking classes. So I take classes, which is why I remember. I every 2-3 months I basically start teaching these topics, and so I never forget them. Otherwise, I would have forgotten myself. Okay. Now, what is the central limit theorem? Okay. So this, let me give you a scenario. So remember here in this example, I told you that this will follow a normal distribution. So how did I tell you that this will follow a normal distribution, right? I told you that this will follow a normal distribution. So why? Because that comes from the central limit theorem. So let's see. So let's say that I roll a dice. Let's say 50 times. Okay. I roll a dice 50 times, and then so my n here is 50. Okay, and then let's say I calculate the probability of 0 successes. Okay, I calculate the probability of 1 success. I calculate the probability of 2 success, and all the way till I calculate the probability of 50 success. Okay, and what is a success? Success means getting a 6. Okay, so let's say I calculate that. So how will I calculate that? I will have to just use the binomial theorem, right guys? I will just use the binomial theorem. So and so let's say I do that. So how will I do that? I cannot do that on paper. It will take a long time to do that on paper, but I can use Python to do that, right? I can use Python to do that. So let's say I do that. So I will write for, so my n is equal to 50, and then I write for I in, what should I write? I have to calculate starting from 0 till 50. So I will write for I in range 51, right? Because this will give me all values starting from 0 till 50, you see? So this is what I have to calculate, right? So I will not print it, I'm just showing you this. Now I will calculate the probability. I'll calculate the probability of getting 0 success. How do I do that? We have seen it already. I'll use binom dot probability mass function. Then I will write the value of r first, which is I in this case, right? Which is I in this case. Then the value of n, which is n. I can write n because n is a constant, and then I will write the value of probability. What is that? 1 by 6. Okay, so this is what I will do, and I will store it in some variable. Okay, let me store it in some variable. So let me say this as result is equal to open close braces. So empty list I have created, and then I will write result dot append. I'll append my results here. Okay, I will append my results here. So now if I run this, I will get the probabilities. So let's see how they look like. So my result looks like this. So the probability of getting 0 success or 0 sixes is this. The probability of getting 1 is this, 2 is this, 3 is this, and so on. And this is the probability of getting 50. Okay, this is the probability of getting 50 sixes. In just a minute. Okay, yeah, so I have this. Okay, I have this now. So what is this list? This list gives me the probability. It gives me the probability of uh, all number of successes starting from 1, starting from 0 till 50. Okay, when I toss a coin, when I toss a dice, when I roll a dice 50 times, what is the probability of getting 0 sixes, 1 6, and so on? Okay, now let me try to draw a histogram for it. So I will write plt. Okay, first I'll have to import it. Import matplotlib dot py plot as plt. Okay, I import this. It'll take a while to run. I see this star here, and then I will use plt dot hist to draw a histogram, and I will write result here. 1 second. Okay, so I have this right now. Okay, I have this. Now let me show you. Now what do I do now? Now I have to repeat this operation many times. Okay, so this is what I have now. Now what I will do, I will repeat this. So here what did I do? I tossed. So what have I done here? If you see carefully, I just found the probability of 0 success and I noted it down. I found the probability of 1 success, I noted it down, and similarly 2 success, noted it down, and so on. Now what I will do, I'll repeat the entire operation. I will repeat the entire operation a large number of times. Large number of times. Okay, I will repeat this entire thing large number of times. What does that mean? So let me repeat it. How many times? Let me repeat it, let's say 100 times. I will repeat this entire thing. So calculating 0 successes, I will repeat this 100 times. So I will get 100 probabilities. Do you follow, guys? I will get 100 probabilities. Similarly, probability of 1 success, I will get 100 probabilities. Similarly, here also I will get 100 probabilities. So everywhere I will get 100 probabilities because I am repeating the entire thing 100 times. Okay, so let me do that. So how do I do that now? So I'll have to write another loop to do that. Okay, I'll have to write another loop which goes from 1 to 100, and within that loop I'll be doing this. Okay, so let me just do that. Okay, okay, so where's my notebook? It is here. Yeah, so right now this is what you get when you roll it once. So roll the dice once, then this is what we get, right? Because I have rolled it only once. Then these are the probabilities I have calculated. Now I'll roll it. Let me plot it instead. Okay, let me just copy and paste this here, and I draw the histogram here itself. So plt dot hist result. Let me put a colon, semicolon here so that I don't get this. So this is how it looks like. Okay, now I will do this more number of times. Now roll the dice. Let's say, okay, what did I say earlier? I said that I will roll it 100 times. Before that, let me roll it 10 times. So I'll slowly increase the number of times I roll. Okay, so once again I'll explain you once again, but let me first just do this. So I'll do this and I'll write an additional loop here. Okay, I'll write an additional loop. Okay, so here I will use for I in, I'll write, let's say, range. I have to roll it 10 times, so I'll write 11. Range 11 means it will roll from 0 to, and I'll keep this inside. This will go further with one indentation, and I'll be 1 second. This result will be a loop. Let me call it result underscore 10. Okay, just to give a different name. This will be result underscore 10, and this will be result underscore 10. So it will keep on doing it. Okay, it will keep on. If you see the value of result underscore 10, the length of it, it will be 561. So that means 50 into 10 times. So it should be 500. Why 561? So for I in range 11, okay, I should have given range 10. And this is 50 only. I can, okay, let it be, it's okay. Okay, so this is how it looks like. So this is when I roll the dice 10 times. Okay, now I'll roll it even more times. I'll roll it, let's say 50 times. Okay, I'll roll it 50 times. So instead of range 10, I will write range 50. And let me call this, instead of 10, I'll call it 50. 50, 50. Okay, okay, so let me do it 500 times. So it will take a while to run. Okay, just give me a minute, guys. I think I'm doing something wrong. Just give me a minute. Okay, so I found this where I have already done it. So let me show you here directly. Okay, I think I slightly confused there. Okay, so what do I have here? So this is again simple. This is I'm importing the same function, and this is the binomial function. Okay, what we have already seen, and we have seen this. What is the probability of getting 13 or more heads if a coin is tossed 20 times? So we all know how to find this. We can use the binom function, binom.pmf, and you can find this. Okay, so this is done. Now let's come to the central limit theorem. Okay, this is the central limit theorem. Let's see what it says. Okay, so first let me explain you the theorem, and then maybe I'll show you the proof. Okay, so previously I was showing you the proof first and then the theorem. Let me first tell you the theorem. Okay, so what does the theorem tell you? The theorem tells you that whatever the distribution of population, okay, so population here is nothing but the data. We are talking about the data. So it tells you that whatever is the data, whatever data you have, be it a normally distributed data, be it any kind of distribution, okay, but the central limit theorem tells you if you take large number of samples, okay, taking a sample from the data, so your data might be let's say getting 10 heads from when you roll a dice 50 times. Let's say that is your data. if you roll if you roll a dice 20 times, how many times, or what is the probability of getting 6 heads? That is your data. Okay, so if you take large number of samples from your data of size greater than 30, okay, of size greater than 30 observations, so you will have to take greater than 30 observations. The mean and the sum of the sample will follow a normal distribution. So let me explain you now with the proof. So I have imported the random function, then obviously this is for plotting, and you can ignore this. This is not needed. Okay, this is not needed in Python 3. It was for Python 2. Okay, so what have I done here is rand integer will gives you, it generates a random number. Okay, it generates a random number between two integers using a uniform distribution. Okay, so what have I done here? I have taken an empty list. And then what have I done here? I have taken a range of this large number. What is this? This is like 10 lakhs. Okay, this is 10 lakh. So I'm generating, so I'm going in a loop 10 lakh times, and each time I go into the loop I'm generating a random number between 100 to 1000. This is what this function does. Random.randint generates a random number between two numbers. Okay, so this will generate one random number between 100 and 1000, and this is inside a loop, which the loop goes from 1 to 10 lakh. So that means I am generating 10 lakh random numbers between 100 and 1000. Okay, I am generating 10 lakh random numbers between 100 and 1000 and storing it in X. Okay, and then I am plotting it. So when I plot it, it looks something like this. Okay, and this makes sense also because random.randint will generate random numbers from a uniform distribution. So these numbers will come from a uniform distribution. So obviously when you plot it, it will look like a uniform distribution. Okay, so that's what it does. Do you follow this, guys? Do you follow this piece of code? No? Do you follow this, guys? What is this piece of code doing? Let me do it here. Okay, so I've written here x is an empty list here. X is an empty list, and then I do it. Let me do it 1 lakh times. 10 lakhs is a lot. Okay, and then I append it to x, and then I plot a histogram for it. Okay. Oh, random is not defined. Let me import it. Oops. Oh, sorry, I was on mute, guys. Okay, so this is my population. Now what do I have to do? I'll select some random samples from the above population. Okay, and how many samples should I select? Large number of samples. Okay, so let me select 50 number of samples. So I'll randomly pick 50 values from here. I will randomly pick 50 values from this variable x. Okay, and the size of the sample should be greater than 30. That's what the central limit theorem tells us. Okay, the size of the sample should be greater than 30. So that means your x, what is your x now? Let me write it down here. So what is x? So x here is the population has which has 1 lakh numbers from 100 to 1000. Okay, okay, and this population this population follows a uniform distribution. Okay, all of you understand, right? This x, right? Is this clear? Do you understand this? Whatever is in this cell, do you understand? Do you understand whatever is in this cell? So you have just created a population. Okay, now what will we do? Now as per the central limit theorem, I will take samples from here, samples of size 30 or more. Why 30 or more? Because that's what the theorem tells us. Okay, so how will we take sample? We will use the function sample. The function sample, what it does, it selects as many samples as you want from another variable. Okay, so let's say my variable is 1 2 3 4 5 6. This is my variable and I want to select 3 samples from here. So I will write, oh, the sample function also comes from some, okay, it is random dot sample. Okay, so I will write random dot sample. Okay, so first let's understand what does the sample function do. What does it do? So I have written 3 here, right? That means it will select randomly 3 variables from here, from this list which I have given. So it has selected 3 1 and 5. If I run it again, it will give some other variable. See, if I run it again, it will give me some other 3 variables. So the random dot sample function, it selects as many variables as you write here as the second input from a population. So your population here is very small. It has just these 6 numbers and you are selecting randomly 3 numbers from this population. So it will randomly select any 3 numbers and give you. Okay, so I hope this random sample function is also clear. Now what will I do? Let me write down what will I do. I will select a large, I will select a large number of sample, okay, each of size at least 30 from the above population. Okay, so from the above population, which is nothing but x, from this population I will select large number of samples. Okay, let me write it. I will randomly select, not, I will randomly select large number of samples, each of size at least 30. Okay, so let me first, so first I will, let me first select only, so first let's select only 10 samples, each of size 30. So how do I do that? For I in range, I will write, for I in range, I have to select only 10 samples, so I will write 10. Okay, and then I will write, I will use the sample function. I will use random dot sample, and then I will write my population, which is x. X is my population, and how many numbers do I want to select from here? Of size 30. So I'll give 30 here. Okay, I'll give 30 here, and let me store it somewhere. I will call it result is equal to this, and I'll store all of this in result dot append. I'll store it here. Okay, and then I will plot it. Plt dot hist. I'll plot result. Give this. Okay, so this is how it looks like. Okay, so now this is, oh, why is it colorful? Did I do something wrong here? Random dot sample x. It is x, right? Yeah, this is my x. So it is selecting 30 and it is storing here. Why is this colorful? It should be in one color, right? I'm just drawing a histogram. I think it is because of, what is wrong? Sorry, I forgot. Yeah, I have to take the average here, not this. Okay, guys, 1 second. Central limit theorem tells me that the average, not the values. The average will follow a normal distribution. So I'm doing it on the values. So now I'll have to actually calculate the average. Okay, so this is what it tells me. Whatever the distribution of population, if you take large number of samples of size greater than 30, the mean and the sum of the sample will follow a normal distribution. So I'll have to calculate the mean here. Okay, so one second. So let me calculate the average. So instead of appending this to your result, I will append the average of that. So I will write np dot mean here, and I will append the average to result. Okay, and then I will plot the average. So the result now has the average. Np is not defined, so import numpy as np. So I'll run this and give a colon here. Okay, now this is how it looks like. Why it doesn't, so it still doesn't look like a normal distribution. Why? Because the algorithm tells me that if you take large number of samples, I haven't taken large number of samples, I have just taken 10 samples. Okay, let me increase this to a large number, let me make it 100, and I run this. Now almost like a normal distribution. Let me make it even large, 1000. Now you see, it's very well like a normal distribution. Let me make it 10,000. Now you see, it's definitely like a normal distribution. Now you just draw a curve on it and it will look like a normal distribution. Okay, I can make this. So 30 is the minimum the algorithm tells me. Let me make it 50 and run it once again. Now you will see it will be like, this is exactly like a normal distribution. Okay, so let me explain you that now. Okay, so I know I messed up here a bit. Let me explain you. So let me go back to this sheet. Okay, okay. So the central limit theorem, let me open up a new sheet, something like this. Okay, so I'll write here the central limit theorem. Okay, so what does this tell you? This tells you no matter what population you have. Okay, so what does this mean? No matter what population you have, this means that it doesn't matter what kind of a distribution your population has. It can be normally distributed, it can be uniformly distributed, it can be any other distribution. Okay, so no matter what distribution your population has, if you take a large number of samples, okay, so from your population, which can be any distribution, if you take large number of samples of size greater than 30 each, okay, so each sample should have a size greater than 30. Okay, if you take samples of size at least 30, the average and the sum of those will always follow a normal distribution, will always follow a normal distribution. So let me explain it with an example. So the example is that, let's say you have a uniform distribution. Okay, you take numbers from 0 to 100. Okay, this is your population, and you have, let's say, thousands of number. You have thousands of number between 0 and 100. Okay, you have, let's say, 10 lakh numbers. You have 10 lakh numbers between 0 to 100. Okay, and they all follow a a uniform distribution, which means the number of times you have 1 in that population is the same as the number of times you have 2, is the same as the number of times you have 3, because you see there the bars are of same height, which means that each number is present in this population the same number of times. The total length of the population is 10 lakh, which means there are 10 lakh numbers. Okay, which means there are 10 lakh numbers, and each number is present the same number of times. So if one is present 50 or 500 times, two is also present 500 times. Excuse me guys, I'm sneezing a lot. Okay, so now what? Now it tells you that you have to take large number of samples from this population. Okay, so let me just take one sample first. I will take my first sample. So how do I take a sample? I will use the random.sample function. Okay, so I will use random.sample. This takes two inputs. First is the population, and next is how many numbers do you want from this population. Okay, so I want at least 30 numbers. So large number of samples of size greater than 30. So let me just take 30 for now. Okay, so I will take 30 only. So I will take 30 numbers from this population, and let's keep this population as x. So I'll write x here, and I will take 30 numbers from this population. Okay, this is my first sample. And what does it tell you? It tells you you have to take a large number of samples. So this is my first sample. Similarly, I will take a second sample also. The same thing. Similarly, I will take a third sample, and I will go on until I have large numbers. Okay, that large number may be, let's say, 100. You have 100 samples now. Okay, you have 100 samples now. Now what does the central limit theorem tells you? The central limit theorem tells you that if you take the average of each of them, the average of each of them, so this first sample will have how many numbers? It will have 30 numbers. Second sample will also have 30 numbers, and so on. You take their average, whatever is the average. So take average. So x bar 1, this is x bar 2, x3 bar, and so on till x 100 bar. So you have 100 numbers now. Now if you plot those 100 numbers, that will follow a normal distribution. That's what the central limit theorem tells you. Okay, so remember, the population was not normally distributed, but if you plot the average, if you plot the average of the samples, okay, it will follow a normal distribution. Okay, that is why previously I had mentioned that this will follow a normal distribution. So that's what I have tried to prove here. So the same example which I just explained, I have done it using Python. So I'm taking, so here the population I have given the population here, which you all understood. I have just taken 10 lakh or 1 lakh numbers, and each number is between 100 and 1000, and these numbers, they follow a uniform distribution. So this is your population. Now what I have done, I will take samples now. So how many samples will I take? I will take 10,000 samples. Okay, I will take 10,000 samples. I have started a loop which runs 10,000 times, and inside the loop, what am I doing? I am taking a random sample from the population above, and I am taking 50 numbers from that population. So in the first iteration, what will happen? 50 numbers will be picked from here. So between 100 and 1000, 50 numbers will be picked, and then the average of those 50 numbers will be calculated. Okay, the average of those 50 numbers will be calculated. So I'll get one number in the first iteration, and that one number will be appended to result. Okay, now the second iteration will start again. 150 numbers will be calculated, 50 random numbers from here, and the average of those 50 numbers will be calculated, and that will be added to result, and this will go on 10,000 times. Okay, so finally my result will be 10,000 numbers. Each number will be the average of some sample. Okay, and then I plot that result. What I get is I get finally a normal distribution. Okay, I finally get a normal distribution. So this is what the central limit theorem tells you. Remember, the population was not normally distributed, but the solution that we got, or the distribution of the averages that we got, it follows a normal distribution. Similarly, not only the average, the sum also follows a normal distribution. So if I repeat this for sum, so instead of mean, let me write sum here. So np dot sum function, if I use, even that will follow a normal distribution. So this is the sum. So if you see, the sum also follows a normal distribution. Okay, so this is the central limit theorem, guys. It is very important as a concept. We will see its application when we learn about linear regression and logistic regression. Okay, but for now, just try to understand the concept. Okay, so let me just write it down. Let me just write it down here. So it tells you, no matter what population you have, okay, if you take large number of samples of size at least 30 each, okay, the average and the sum of the samples will follow a normal distribution. Okay, this is the central limit theorem. Okay, so again, giving you an example. So if this is the distribution, let's say it is something like this. Okay, you have numbers starting from 0 to 100. Okay, so these numbers are present more in the data, right? The histogram is, this is what it tells you, that the numbers between 0 to 10 are present more, and the numbers after 10 to 100 are present less in the data. So let's say this is your x, this is your population. So the numbers between 0 to 10 are present more. You see, their height is more, the height of these bars is more, which means these numbers are present more in data, and the numbers after 10 are present less in the data. Okay, so this is your population. It is not normally distributed. Now, what does the central limit theorem tells you? You take large number of samples. So let's take sample number. Okay, this is 1, 2, 3, 4, and we go on till 100. So we take 100 samples from this data, and each sample has a size of, let's say, 50, because we have to take at least 30. So let's take 50. So that means we will generate 50 random numbers from here. Okay, so generate 50 random numbers. So 1, 2, 3, and so on till 50. Okay, so 1, 2 till 50. Similarly, for the second sample also, generate 50 random numbers. So again 50 random numbers, and so on. Okay, so 1, 2, 3, and so on till 50. So we generate 50 random numbers from this population each time. Okay, so 100 times we generate these 50 random numbers, and then what we take sample average, and we take sample sum also. So these 50 numbers that we have got, we take their average. So let me call it an mu1, this is mu2, and so on till mu100. Okay, similarly I calculate the sum, so s1, s2, and so on till s100. Now the central limit theorem tells us that if you plot these 100 averages, or if you plot these 100 sums, they will follow a normal distribution. Okay, so these if you plot these will follow a normal distribution. Similarly, if you plot these, this will also follow a normal distribution. So that is what the central limit theorem tells us. Do you follow, guys? Do you follow? So we will see the application of this sometime maybe next week or next to next week. But for now, just understand that this is what the central limit theorem is. So understand each line of the theorem, okay? And then you will be able to follow. Don't confuse with this large number of samples. This can be any large number, okay? So if you generate just two samples, you will just have two averages. So if I don't do this 100 times and I do it just twice, then what would happen? I will just have two numbers. I cannot draw a histogram for just two numbers. It will be a something like this, because there will be just two numbers. So I need to generate more numbers to be able to draw the histogram, okay? So this has to be something large so that you can draw the histogram, okay? The only thing the algorithm says is the sample size should be at least 30. Don't take a sample size which is just 10. Then you may not get a normal distribution. So make sure that the sample size is large. Okay. So this is one of the difficult things to understand in stats. Okay. So any questions, guys?